clarify just before I start that this isn't actually my field of expertise, for loss of a better phrase. I'm actually studying physics, but this is something that I've had quite a passion for ever since I was a child. You know, everyone goes through that dinosaur phase. I presume so anyway. So this is just something I've been doing background reading on in my own spare time, so I thought I'd share it with you all. So I think it's first make an important clarification that extinctions are a natural part of evolution. It's, the majority of species, approximately 99% of that have ever existed, have already died out. A prime example of this is the Stegosaurus and Diplodocus, which are dinosaurs which didn't actually die out in the mass extinction, but they just went extinct from their own natural causes beforehand. The causes of extinctions, like local extinctions, are usually small things such as a lake drying up or invasive species appearing in the environment. A great example of this is when the land bridge opened up between North and South America, which led to a sizable amount of extinctions in the large dominant groups in South America. But scientists have been able to look at the fossil record and give a rough estimate of what is known as the background rate of extinction. This is guessed to be around, guessed is a bad choice of word, this is estimated to be around 1 to 5 species per million per year. We've got to bear in mind though this is very approximate, as a lot of species won't leave evidence in the fossil record, and of course we do not have a complete record of every animal that's ever died out, so that's why there's such a large margin of error there. Now, as to the history of the idea of mass extinction, it's actually comparatively recent, much more so than people think. It was only popularized after the 1970s. So this is actually fairly recent. We all kind of take for granted that facts like the dinosaurs died out in mass extinction, but it hasn't been that way for very long. Now, before that time, there was very little evidence for such mass events, and it was always assumed that they died out very slowly over long periods of time. Now, after the 1970s, the rise of plate tectonics and impact geology gave rise to the concept of the Earth is not static as we always assumed it would. It was. And then, building on from that, there were paleontologists such as Norman Nuer, who managed to build cases for periods of relatively rapid extinction throughout the fossil record. And then the big breakthrough came in 1980 when the Cretaceous impact hypothesis, which is the demise of dinosaurs, was first suggested. But it still took another decade after that for the idea to actually gain weight in the academic community. So we're only looking at around 1990. That's only 21 years that the theory of mass extinctions has actually been propagated in the scientific community. So it's surprisingly recent. Now, what is a mass extinction? Well, as we already established, there's a background rate of extinctions, so that's 1 to 5 species per million per year. But of course, this isn't actually at an even rate. It varies up and down across periods of time. And occasionally you get brief periods where it's extremely high rates of extinction. But got to clarify, it is actually a very ambiguous term. There is no set-in-stone definition used throughout the academic community. It varies quite substantially. But they are generally characterized by a couple of factors, such as a large and rapid decrease in the abundance and diversity of macroscopic life. Now, I've got to clarify here, it's macroscopic life as opposed to microscopic, and the reason for this is that the majority of microscopic life forms do not leave substantial evidence in the fossil record, and so it's very difficult to determine extinction rates for any creatures that do not leave enough evidence for us to trace them by. And so generally, mass extinctions only focus on the complex portion of the biosphere. But generally speaking, for a mass extinction, the most general definition I could find was around 40% of all genera going extinct in a period of roughly 10 million years is what generally characterizes a mass extinction. Now, throughout the fossil record, there are around 20 extinctions which can be considered mass. But of these, 5 of them stick out very prominently amongst the crowd. Now, these are ones where over 50%, sorry, I should say 50, ignore the error. This is where over 50% of all genera have become extinct. And these have been known colloquially as the Big Five. So I've got a beautiful little diagram there, not sourced from Wikipedia in the slightest, which illustrates the percentage of genera over the period of time since the Cambrian explosion. all the the big five mass extinctions are indicated by the yellow triangles. Now, amongst these, two of them stick out very prominently. And these are the Cretaceous mass extinction, which is the demise of dinosaurs. This sticks out very prominently because of the spectacular speed at which it occurred, which is very distinct from all the other mass extinctions. And the other one which sticks out is the Permian-Triassic Extinction, because it was so incredibly catastrophic. Whereas the others, you can see here in the table, you've got the others which are between 50 and 60% of genera going extinct. You've got the Permian-Triassic with 83% of genera, so that's a very large increase, and so it warrants explanation. So I'm just going to go into a bit more detail on those two specific ones. Because I'd love to talk about dinosaurs, we'll start with this one. So, Kt Extinction event was about 65 million years ago. And so it's the best known and most well studied of the five big extinction events, because there's much more evidence for this event being so recent. Now, it's characterized by the demise of the non-avian dinosaurs. Everyone knows those, your Tyrannosaurus rex, your Triceratops, the classics. But there are also many other important groups which also disappeared, such as the pterosaurs, mosasaurs, plesiosaurs, trilobites, and giant crocodiles such as Sarcosuchus. But also should point out that though many people assume that birds and mammals got through this extinction unscathed, it's not true. There are actually a substantial portion of bird species, the non-neornithians, which became extinct, and also many major mammal lineages suffered heavy losses, but all came through unscathed overall. And it's also important to talk about the percentage of plant life which is destroyed, because we commonly only think about mass extinctions in terms of animal life. But as you see here, in North America, we lose 57% of species in North America. So it's also quite a substantial decrease in the plant biodome as well. Now, the causes for the Kt extinction were first established in 1980. But up to that point, it had been assumed that they just died out slowly due to cooling climates. Now, it was Louis Alvarez and his colleagues who first discovered the evidence for this. And what they were actually doing was looking for a method of creating a geological clock using an element called iridium. Now, iridium is very rare on Earth on its own, and it's usually only brought here by meteorite impacts. And so what they aimed to do was to be able to determine the age of sedimentary rocks by levels of iridium in them. Now, this worked remarkably well at rock layers before 65 million years ago and after 65 million years ago. But at the boundary, they found an anomalous spike in the iridium levels. It was incredibly large, much more than they were predicted. And so they had two conclusions they could have drawn. The first one is that these rocks were laid down incredibly slowly, at an unnaturally long period of time. And they went for the second option, which was a giant impact at the 65 million years ago point, which delivered substantial amounts of iridium. Now, this was initially scorned by the academic community, because there was drawn a fairly remarkable conclusion from very modest evidence. But nonetheless, they continued with their theory and hypothesized it would have to be a 10-kilometer wide asteroid which had impacted the Earth in order to cause an iridium spike of that size. Now, as study into this progressed, more geologists around the world found similar evidence for such iridium spikes, as well as such evidence as shocked quartz crystals in some locations around the world, which can only be formed by impact by meteorites. And so this hypothesis soon became well established as a major contributor to the demise of dinosaurs. And eventually, the actual impact crater was discovered at Chicxulub in Mexico, which is right there. It's a 140-kilometer wide crater, so incredibly large, and exactly as they predicted would be thrown up by a 10-kilometer wide asteroid. Now, the implications of this asteroid impacting would have been, in the immediate blast zone, tidal waves, incineration, and shock waves. And in the longer term, there would be a huge amount of ash that would have been thrown up into the atmosphere, causing substantial global cooling over a very short period of time, which the dinosaurs would have been unlikely to adapt to. But there are some other causes which have also been suggested. Now, few people think that the actual impact crater at Chicxulub was not a cause, but many people propose a multiple cause scenario. Now, another possible cause is the eruption of the Deccan Traps in India, which is a large flood basalt formation, which would have, again, produced huge amounts of volcanic ash, contributing to global cooling. Now, there was also the concept of a sea level regression in the late Cretaceous, which would have resulted in a loss of many low-level and shallow marine environments. And there's also a much more controversial theory, which is that of a multiple impact, in which a much larger asteroid than the 10-kilometre one hypothesized by Louis Alvarez and team also impacted around the same time. And there is some evidence for this. There is a 600-kilometre wide crater off the coast of India, although this has come under scrutiny in recent years, and it's also been suggested it may just be a depression feature. So as of the moment, it is widely acknowledged that the Alvarez team were right, and it is in fact an impact that caused the demise of the dinosaurs. Now I just want to talk about the Permian-Triassic mass extinction for a moment. Now this one is the one where 83% of genera died out, which is a catastrophically large amount, and it has led to it being termed as the Great Dying. Now, there's two major factors contributing to the demise as part of this extinction. It was the collapse of both the forests and the reef ecosystems, which are both major hubs of biodiversity. Now, the fossil record has shown that around 99% of plankton and 96% of coral genera became extinct at this point. And there's also the famous coal gap in the early and mid-Triassic, just after the Permian, which suggests that no forests have become well established in the stages immediately following the extinction, to the point at which they could provide coal. Now, there's a couple of species that are most prominent when they died out: the trilobites, the eurypterids or sea scorpions, and also many of the mammal-like reptiles which had dominated the land prior to the extinction, such as this Gorgonopteryx. Now, it was initially presumed that the only cause for this event could be another giant impact similar to the Cretaceous Tertiary extinction event, and much work was put into actually finding evidence for such a thing. But so far, nothing has been provided, and so we had to search elsewhere for evidence pointing towards the cause of such an event. Currently, the most prominent theory that is backed by the best evidence is the eruption of the Siberian Trap Formation in Siberia, Russia, which is another example of a gigantic flood basalt eruption. This would have led to huge release of sulfur and carbon dioxide. Sulfur dioxide would have led to flash cooling over very short periods. And the carbon dioxide over the long term would have resulted in substantial global warming. And so you have this incredibly fluctuating climate over the phases immediately following the eruption, which few animals would have been able to adapt to. Now, the rocks from these eruptions are still seen today. They actually form the Siberian Traps Formation in Russia. Just to give you an idea of the size, that's the amount of lava that was pumped out by this eruption. And that is an area roughly equivalent to Western Europe today. So it's a huge amount of material that was deposited by this volcanic eruption. And so you can get an idea of just how much ash would have been produced into the atmosphere. Now, there are a few other causes which are also hypothesized in tangent with this volcanic scenario. But one of the first ones is the oceans becoming anoxic, which means they became deprived of oxygen, which may have been a major contributing factor in the collapse of the marine ecosystems. This anoxic ocean would also have led towards a huge production of hydrogen sulfide due to an imbalance between the photosynthesizing plankton and sulfate-producing bacteria deeper down. And so again, you have this giant release of hydrogen sulfide, which leads to substantial global cooling. And one of the other causes is the formation of the supercontinent Pangaea, which was just in the map back then. And when all the continents combine into one supercontinent, it causes substantial disruption to the ocean circulation and thus the climate systems. And so while this may not have been an overriding factor, it certainly could have contributed in the long term. Now, as for the recovery of life after a mass extinction, generally it only takes a few million years, so this varies very much dependent on the actual scale of the extinction. With the Cretaceous tertiary extinction, within 5 million years or so afterwards, animals and plants became quickly re-established. Permian-Triassic extinction, by comparison, it was around 15 million years before life could become properly established again. When ecosystems collapse, this leaves large niches newly available for new animals to come and colonize. Of course, mammals are a prime example of this. We are one of the most prominent examples of creatures filling a niche. Now, the niche we filled was that left by the dinosaurs. Indeed, mammals existed for the entire period of the dinosaurs' reign, but they were forced into marginal groups as dinosaurs occupied all the major points in the ecosystem. Although I should point out that once dinosaurs had died out, it was far from a foregone conclusion that mammals would actually take over. And indeed, for about 30 million years after the extinction, giant birds and crocodilians actually were the top predators in the environment. And such birds as this one, Gistornis, actually preyed on primitive horses. Right there, not around there. But after the Permian extinction, it was a much different scenario. We actually had disaster taxa becoming the dominant land groups, and these are hardy creatures that were very adaptable and capable of surviving in a tough environment. And Litrosaurus was the prime example of this one. It's not a dinosaur, it's just a similar archosaur reptile. But at some point in the early Triassic, it actually was contributed to 90% of all land vertebrates. I think this is the only time one species has been so incredibly successful at colonizing the entire continent. And it was around the mid-Triassic before dinosaurs actually took over from these groups. Now, many people have hypothesized that there must be some sort of common pattern with these extinction events, particularly early on in their discovery. But people pointed to the fossil record and tried to find evidence for, say, every 25 million years or so, there would be a mass extinction of creatures. However, this evidence is largely doubted at this stage. One of the more prominent hypotheses in its early days was that of a Death Star called Nemesis, which actually floated near to our solar system every few million years and would perturb the meteorite clouds around the outskirts of our sun, and would thus send hundreds of thousands of meteorites spinning through the solar system. But now this is widely doubted, unfortunately. I'd just like to point out I did resist the urge to put a Star Wars reference in there. But, now it's widely accepted that each extinction event is actually unique, has its own unique cause and its own unique time frame, and there is no common pattern in that respect. However, there are common patterns in the results. Generally, species of a large size, limited distribution, large population, and so on, will be fairly poorly adapted to surviving such a global extinction event. And generally, the survival will be dependent on species that have a wide distribution and very adaptable to the environment. The best example is how easy it was to wipe out the dodo compared to wiping out the rat, for example. One would be much harder than the other. Although some people, such as Mr. D. Brown of the University of Chicago, have characterized the death of a species as due to bad genes, or bad luck, as opposed to bad genes. And what he's implying there is during these large extinction events, the normal rules of natural selection actually break down, and it purely becomes a question of luck. And for instance, with humans destroying environments like we do today, if an entire ecosystem is destroyed, it's very difficult to say one species within that ecosystem will have a larger chance of survival than any other, regardless of how well adapted they are for that particular ecosystem. So speaking about humans destroying the habitat, it's commonly said that these days we are actually living through a sixth large mass extinction, which is known as the Holocene extinction, which has been occurring since around 10,000 BC, which is roughly the end of the last ice age. Now, it's suggested that the main cause for this are a combination of climate change, which is attributed to the slow global warming since the last ice age and the current interglacial, and also human impact in way of hunting and destruction of the environment. Now, it's characterized by the disappearance of so-called megafauna, and some good examples of this, such as the Steller sea cow, the giant sloth lemurs of Madagascar, the quagga, and a bit closer to home, the house eagle and the moa, which are very recent compared to the others. Now, so far it's been documented that 876 species have become extinct between 1500 and 2000. But it's important to bear in mind that a large majority of extinctions actually go undocumented. So the actual value could easily be 10 times this number. But the general consensus in the scientific community is actually that we are indeed responsible for the current mass extinction. And so, thank you for listening. Any questions?